Hello student, last class we have discussed what is Ampere cycle law and its application, how to find magnetic field strength due to hollow and solid infinite long cylindrical wire. Here now, here we will discuss how to find magnetic field strength inside a solenoid and how to find magnetic field strength inside a toroid. Clear? By using Ampere cycle law. So first we will discuss what is solenoid. Solenoid means, suppose we have a non-conductor or we have a insulator. Suppose this is a insulator and this is insulating material or insulator or non-conductor. Now we have a wire, insulating wire, which wounded over it. Suppose this is the wire which wounded over insulating material in such a way that it is look like a cylindrical coil, like this. Clear? So this is insulator or insulating material, that means non-conductor, and the wire, the insulating wire which is wounded over the conductor, non-conductor, that means this make a solenoid. So this is the helical structure. So what is helical? That means we have a spring. Suppose it is like a spring and this is the number of turns, and these turns are very close to each other, and this look like a cylindrical coil. And there is a large number of turns which is consist very close to each other, and their center are coincide, and this circle, this form a circular loop, and this turn also form a circular loop, and this turn also form a circular loop. That means these are concentric circular loop, and there are number of turns. So this make this is the form of a solenoid. Here, and you can take, this is the length of the solenoid. So length of the solenoid L, and this is the radius of the solenoid. Clear? And this is axis of the solenoid. This is axis of the solenoid. Clear? Okay. Now here we will discuss what is ideal solenoid. So solenoid means it consists number of circular turns, and these turns are very close to each other. So which form a solenoid, and this look like a cylindrical coil. That means this look like a cylindrical coil, and the turn of the circular coil look like a helical structure. Helical means just like a spring. So this is the structure of a solenoid. Clear? Okay. If we connect here, this is positive terminal. This is positive terminal and this is negative terminal, and there is a key. This is negative and this is positive terminal. So this is a solenoid. So first we will discuss about what is ideal solenoid. Ideal solenoid. Here we will discuss about ideal solenoid. Ideal solenoid means this is length of the solenoid L and radius of the solenoid R. So for ideal solenoid, we have to remember the following terms, the following points. So first point, for ideal solenoid, the length of the solenoid is very large. That means L is very large as compared to radius of the solenoid. This is the first point to remember for ideal solenoid. That means length of the solenoid which is very large as compared to radius of the solenoid. Clear? Second point, the magnetic field strength, the magnetic field strength is very large on the axis of the solenoid and the magnetic field strength is very large on the axis of the solenoid and it is uniform along its axis. That means the magnetic field strength inside the solenoid, is very large and is uniform along the solenoid and it is straight line. That means the magnetic field strength inside the solenoid or inside the ideal solenoid is straight line and uniform along the axis of the solenoid and the field strength is maximum. Why? Suppose for this point, suppose there is number of turns. This is the direction of flow of current. If this is the direction of flow of current, then this is the direction of current. In this way, it's the direction of flow of current through the wire. Clear? Now, we know if there is a current carrying conductor and current flowing through this direction, by using right hand thumb rule, we can find the direction of magnetic field. And the magnetic lines of force consist of a current carrying conductor which is concentric circular loop. That means this is the direction of flow of current, and according to right hand thumb rule, thumb indicate the direction of current, and if you call the finger, then tip of the finger indicate the direction of magnetic field. Clear? So this is the direction of magnetic field in this point inward direction, and here is the direction of magnetic field which is outward direction. The cross indicates the convenience method to remember to determine magnetic field strength which is inward direction, and this is the convenience method to represent the magnetic field which is coming outward. So in this case, the magnetic field for fast turn, which is inward direction, and here outward direction, which make a circular ring. And similarly, another one ring. Suppose we have one ring. This is one ring, one circular ring, and this is the direction of flow of current in this way. For one ring, for one circular ring, the direction of flow of current. If we find magnetic field strength, then we have to use right hand thumb rule. That is the direction of current and it's the direction of magnetic field in this way. The direction of magnetic field in this way. Clear? This is magnetic lines of force for one solenoid. If there is a flow, this is the direction of current, and this is the direction of magnetic field which make a circular ring. And this is the direction of magnetic field for one coil. Clear? Suppose there are another coil also here, second coil. So this is the direction of current in this way. So if we use right hand thumb rule here, then this is also, we can make a magnetic field lines. This is the direction of magnetic field line in this way. Clear? Because these turns are very close to each other. So the magnetic lines of first turn and the magnetic lines of second turn, third turn, fourth, and so on. There are n number of turn. So for n number of turn, the magnetic field inside, this is the axis of the solenoid, because these rings are concentric circle, or concentric ring means the center of each ring along the axis of the solenoid. This is the center of solenoid. Sorry, this is the center of one ring, center of another ring, center of another ring, and if we join all the point of the center of the ring, then this make a straight line with its axis of the solenoid. Clear? So this is the center of one ring. This is center of another ring. Suppose we will take, if we take another one ring. This is another one ring, and this is direction of flow of current. So these are the magnetic lines. These are the graphical representation of magnetic lines and center point. Clear? We know the magnetic field lines are center of a circular coil which is straight line in at point. That means at center of the ring which is straight line. So here the magnetic field lines which is straight line. Here so magnetic field line which is straight line. Due to large number of close pair and these turns are very close to each other. So magnetic field line due to a long solenoid inside the solenoid. This is the direction of magnetic field. Clear? This is straight line and outside the solenoid loop like this. Clear? And we can draw. This is the graphical representation of magnetic field lines for a solenoid. Clear? Because this is the flow of current and this is the magnetic field lines. So for long solenoid, for ideal solenoid means L is very large as compared to radius. So inside the solenoid, the direction of magnetic field which is along the axis and this is straight line and this is very strong. So this is the meaning of this point. Clear? Now next point, third point. The magnetic field strength, the magnetic field strength outside the solenoid is very weak and can be taken as 0. The magnetic field strength of a solenoid, that means outside the solenoid, is very weak and can be taken to be 0. This is assumption. Actually, the magnetic field strength outside the solenoid is not 0. It is very small as compared to inside the solenoid and outside the solenoid. This is inside the solenoid point, inside point, and this is outside point. The magnetic field strength is very large as compared to outside. So if you compare these 2 points, then this point, magnetic field strength is negligible and can be treated as 0. Why? Look at the diagram carefully how magnetic field strength is negligible. Suppose this is 1 turn. First we take 1 turn and this is the direction of flow of current. Then this is the direction of flow of current in this way. This is point A, this is point B. This is upper point A and this is lower point B, because this is number of turns, just like a ring or circular ring. This point A and this point B. Clear? So first point A, suppose we have a model look like this is the flow of current, this is the direction of flow of current, and there is 2 point A, this is point A, and this is point B, and this is the direction of flow of current of 1 turn. Clear? So at point A, if you use right hand thumb rule, then this is the direction of flow of current and this is the direction of magnetic field. This is the direction of magnetic field. In this way, the direction of magnetic field, and which make a circular. Clear? So if you choose, there is a point P. Due to point A, there is a point P here, and this is the direction of flow of current at point A. Due to this point, this is the direction of magnetic field in this way. So this is the direction of magnetic field. So how can you find the direction of magnetic field? First, we have to draw a tangent on the magnetic lines which give the direction of magnetic field. So due to this current element or this small current element at point A, this is the direction of magnetic field in this way, because this is the magnetic lines. So we can write here this point is magnetic field A due to this point. Clear? due to this point is the direction of magnetic field in this way, because it's the straight line which a lambda tangent. Now second point, this point is B. Here this is the direction of flow of current, so in this point is the direction of current. And if you use right hand thumb rule, then this is the right hand thumb rule, and this point is the direction of magnetic lines, because all the magnetic lines are concentric circle. That means this is the direction of magnetic line, then this is also the direction of magnetic line. That means this is the direction of magnetic line, and in this you look like this. And last point, this is the direction of magnetic line. Clear? So due to point B, if you draw a tangent at this point, then this is the direction of magnetic field at point B. Clear? Okay. Look at the point P. At point P, there is two magnetic field. This is the direction of magnetic field due to point A, and this is the direction of magnetic field due to point B. And these two magnetic lines, or these two magnetic fields are which are opposite to each other, and the angle between them is 180 degree. If we use a vector law, then these magnetic lines are cancelled if its magnitude are equal, because these are opposite to each other. If their magnitude equal, because this magnitude cannot be equal, this is a large distance and this is small distance, so this magnetic field is large as compared to this magnetic field, but they can cancel. Clear? They can cancel some of their magnitude. So at point P, the magnetic field strength is very weak as compared to this is central point, as compared to the center of the coil. Clear? So if we imagine, or if we compare these 2 points, then point 1 and point 2, then magnetic field strength is very large, point 1 as compared to point 2. So this is outside point, this is outside point due to one term, second term, third term, fourth term, and number of term. So outside point, this is also outside point, this is outside point. Here the magnetic field strength is very weak and can be treated as 0. So this is the assumption of ideal solenoid. Clear? Okay. So these are the assumption, or these are the assumption for ideal solenoid. So in this case we have to find magnetic field strength inside a ideal solenoid. To find magnetic field strength inside a solenoid. Solenoid means we'll discuss here ideal solenoid. Clear? So look at the diagram. This is non-conductor insulating material, and these are the number of turns which wounded over a insulating material. Direction. Clear? Now look at the diagram. Suppose this is positive terminal and this is negative terminal, then this is the direction of flow of current in this way. Direction of flow of current. Clear? And here we will discuss about ideal solenoid. Clear? Okay. Suppose there are n number of turns, and if we imagine this is the point which is coming outward, and this point the current which is inward, because this is inward direction and this is outward direction. This is also inward direction and this is outward direction of flow of current. Clear? Now if we cut the solenoid from its middle section, then the diagram will be like this. Then this is the point, the current which is coming outward. This is the outward current. And here the cross indicates that the current which is flowing in one direction. And this is ideal solenoid. Clear? Okay. Now look at the diagram. Due to this current element or due to this current in this way over the surface. So due to this current, then this is the direction of magnetic field. So in this way, this is the direction of magnetic field, and the magnetic field inside a solenoid or inside an ideal solenoid is straight line, which is along the axis of the solenoid, because this is axis of a solenoid, and at two end point of the solenoid, this direction is just curve, and here also the direction of, but at axis of the solenoid, the direction of magnetic field which is straight line. Clear? Okay. Now suppose we have a point P on the axis of a solenoid, where we have to find magnetic field strength by using Ampere's circuital law. So now how can we find magnetic field at point P by using Ampere's circuital law? First, we have to draw or we have to imagine a Amperian law. What is, suppose we have a Amperian law. This is Amperian law, and the Amperian law which passing through point P. This is Amperian law. Look like a rectangle. This is rectangular Amperian law, and this point P, the Amperian law which passing through the point P. Suppose this point A and this point A and this point B and this point C and this point D. That is A, B, C, D, A, B, C, D, A. Each A closed Amperian loop, like a rectangular Amperian loop. Clear? And we have to find magnetic field strength at point P. So according to Ampere's circuital law. So what is Ampere's circuital law? That means B dot dl equal to mu naught I inside. Clear? Okay. Now we will come left hand side, that is RHS close integral B dot dl. That means this is Amperian law A, B, C, D. This is the direction of Amperian law A to B, B to C, and C to D, and D to A. Because this form a closed Amperian loop just like a rectangle. So A, B, C, D, and the closed Amperian loop. So you can write that is closed Amperian loop A, B, C, D, A. It is B dot dl. So now look at the diagram. A to B, this is symmetry. A to B symmetry, B to C, C to D, and D to A symmetry, because this is the direction of magnetic field, and if you choose a small length element which is dl, and what is dl? Direction of dl, because the direction of dl and magnetic field are along same line. That means the direction of dl which is along the direction of Amperian loop. So this is the direction of Amperian loop and this is the direction of magnetic field. So A to B, each and every point magnetic field strength is constant, and the angle between dl and D is constant. Similarly, B to C is the direction of magnetic field, and this is, if you choose a small length element, the direction of length element, that is dl, and angle between them is 90 degrees. So B to C is symmetry, C to D, and D to A. So you can write this integration, that is A to B, it is B dot dl plus B to C, it is B dot dl plus B to C, C to D, C to D, B dot dl plus D to A, D to A, B dot dl. So dot product of two vectors, so you know that is A to B, B dot dl we can write B dl cos theta. What is theta? Theta is angle between, if you write here theta is angle between magnetic field and dl element, that is A to B. So from A to B magnet, this is the direction of magnetic field and this is the direction of dl length element. Then A to B magnetic field and dl element are along the same line. So we can write theta is here 0 degree because theta is angle between magnetic field and dl length element. So B dl cos 0 degree. Next B to C, that is B dl cos theta. So B to C, look at the diagram. B to C, this is the direction of Amperian lobe and this is the direction of magnetic field, which is angle 90 degree. If you choose a small element dl, is the direction of dl and the direction of magnetic field and angle here 90 degree. So you can write theta is here 90 degree. Next plus C to D. So C to D, that is B dl cos C to D. C to D means this is the direction of, if you choose a small element, then this is the direction of magnetic field dl. Clear? Okay. But what is B? B means magnetic field strength outside. We know the outside magnetic field for an ideal solenoid, which is equal to, this is assumption, the magnetic field inside the solenoid, which is constant quantity and its strength is large, and the magnetic field which is along the axis, this is axis. So this is axis of the solenoid and it's this straight line, but outside the solenoid magnetic field strength is 0. So this term is, you can write cos theta and this magnetic field is 0. Then this term will be 0. Next D to A, then you can write D to A, B dl cos D to A. This is the direction of Amperian lobe and the direction of dl element, or this is the direction of magnetic field B and the angle between them is 90 degree. So you can write here 90 degree. Clear? Now use the value. What is cos 0? The value of cos 0 which is equal to 1, and here the cos value of cos 90 which is equal to 0. But here C to D magnetic field strength is 0, so total term equal to 0. Then D to A, here cos 90 equal to 0 degree. Sorry, cos 90 equal to 0. So this term 0 we can write, which is equal to integration over A to B, that is B dl, because cos 0 degree equal to 1. Then this term is 0, then this term equal to 0, and this term equal to 0. So finally you can write this relation, that is B dot dl over close integral, which is equal to B dl, that is A to B, B dl. But B to D, A to B means total magnetic field strength is constant, because ideal solenoid, for ideal solenoid B is constant quantity, so we can take it out from the integration. So A to B, that is dl and B dl. So B into, what is dl? dl is length element, so it integration, that is L, or you can write B dl. What is A to B? Suppose the length of the solenoid, the length of the Amperian lobe from A to B, this length is L. This length is L means A to B length is L. That is A to the C to D also length is L, and this length is L, and this length is L. Clear? So from integration A to B, it is 0 to L. Now this term can be write the dl, integration of dl, which is equal to L, integration over 0 to L. So total it is BL. Clear? Now this is left hand side, LHS side. So LHS side equation 1. Clear? Now come to, now this is equation 1 for left hand side. So will come now right hand side of the Ampere circle law, this right hand side. Before going to right hand side, let small n be the number of turn for unit length. Number of turn per unit length. If capital N be the total number of turn, then we can write small n equal to total number of turn by L, total length. Clear? Because n is the number of turn per unit length, so n equal to, we can write what is n? N equal to capital N equal to small n into L. Clear? If there is n number of turn, that is if inside the apparatus if there is n number of turn, then n number of turn can be write that is n into L. What is n? N means total number of turn per unit length. Clear? So now we will come right hand side of the Ampere circle law. So what is right hand side of the Ampere circle law? From this relation, this RHS, what is right hand side? Mu naught times I inside. What is I inside? I inside means total current inside the Amperian loop. This is Amperian closed Amperian loop A, B, C, D, and we have to find total current inside the Amperian loop. Look at the diagram. This dot mark indicates that the current which is flowing outer direction, and these are the outside current of Amperian loop. But inside the loop, this is cross point, and the cross point indicates that the current which is flowing inward direction. That means if this is Amperian loop A, B, C, D, and this cross indicates that is the direction of flow of current, and this dot indicates that is the direction of flow of current. This is outer direction, this is inward direction. So we have to find I enclosed means total current within the Amperian loop. This is Amperian loop, and there are n number of turn. This is the n number of turn. Clear? Suppose for one turn, the current flowing I current. For one number of turn, the total current flowing, that is I. For two turn, that is two turn, total current 2I current. For three turn, 3I current. Similarly, if there are n number of turn inside the Amperian loop, so for n turns, the total current, that is Ni, which is equal to I inside. That means inside the Amperian loop. And if we write this relation, then we can write mu naught times I inside. So mu naught into I inside equal to Ni, capital Ni. But what is capital N? Capital N equal to small n into L. Now, if we write this relation in terms of total number of turn per unit length, so we can write mu naught I inside, which is equal to mu naught n total capital N, that is NL into I. This is equation 2. If we use equation 1 and equation 2 in Ampere circle law, that is B dot dl over cos integral, which is equal to mu naught times I inside. Then what is B dot dl? From equation 1 we can write dl and mu naught into, this is equation 2. So in place of mu naught I inside, we can write mu naught NL I. Mu naught NL into I. 1L 1L cancel. So B equal to mu naught Ni. Which is magnetic field strength inside the solenoid or inside the ideal solenoid or axis of the solenoid. Clear? Okay. If we want to write the magnetic field strength in terms of total number of turns, we can write mu naught capital N by L into I. This is the total magnetic field strength inside the solenoid. Clear? Okay. So if we find the magnetic field strength at two ends of the solenoid, then its value can be right. That is the magnetic field strength at two ends of the solenoid. And this magnetic field strength at last end point of the solenoid. If this is solenoid, suppose this is solenoid, and this is the direction of magnetic field. But here magnetic field strength is constant. But this is the end point, and this is also end point. These 2 points, magnetic field, we have to find total magnetic field strength at end point of the solenoid. So end point of the solenoid, which is equal to the end point, half of the magnitude, half of the magnetic field strength inside the solenoid, which is equal to mu naught Ni by 2. That means the strength of magnetic field at two ends of the solenoid, which is half of the magnetic field inside the solenoid. This is end point. This is magnetic field strength at two end points. Clear? This is all about how to find magnetic field strength due to a ideal solenoid by using Ampere's law. So now we will come across the term what is toroid, and we have to find magnetic field strength due to a toroid by using Ampere's law. So look at the diagram of toroid and what is toroid. Suppose we have a hollow circular ring. This is a hollow circular ring, and the coil which is wounded over the circular ring this is a turn. The number of turn over a hollow circular ring which form a toroid. This is the model of a toroid. Clear? This is the model of a toroid. This is the model of a toroid. That means this is a hollow circular ring, and the coil which is wounded over it, and this coil are very close to each other. This is the model of a toroid. That means we know what is solenoid. Solenoid means this is look like a, suppose we have a non-conducting material or insulator, and the number of turns is wounded over it, and this make a solenoid. And solenoid look like a cylindrical coil. If we bend this solenoid, then the solenoid look like this, look like a circular ring. That means if we bend this solenoid in the form of a ring, then this ring is also known as a toroid. Clear? So this is the toroid. So in this case, we have to find magnetic field strength. We have to find magnetic field strength of a toroid. Clear? Okay. Look at the diagram. This is the center point of the toroid, and this distance, suppose this distance is capital R, and this is the thickness of the toroid. Suppose this thickness is D. And what is D? D means thickness of the toroid, and R means radius of the toroid, and this is the radius of the toroid. But here we will discuss about ideal toroid. That means ideal toroid. So what is ideal toroid? Ideal toroid means if we compare the radius of the toroid, this is greater than D, very large as compared to thickness of the toroid. That means the thickness of the toroid is very small as compared to R. So this is the actual form of ideal toroid. Clear? And this distance, the R1, and if choose this distance R2, here R1 and nearly equal to R2. That means this distance D, the thickness of toroid D is negligible. So this is also known as a ideal toroid. So here we will deals about a ideal toroid. Clear? Okay. Now we have to find the magnetic field strength. Magnetic field strength due to a toroid. Magnetic field strength due to a toroid. So toroid means it is the ring shaped solenoid, and this is the hollow ring shaped a non-conductor, and the coil which is wounded over it, and this coil are very close to each other. Clear? Okay. Now if we cut the toroid from its central part, if we cut this toroid from its middle section, then the final diagram will be, then this is, suppose this is the direction of current I, in this way the direction of current, this is the direction of current. Clear? Okay. That means if you choose this point, the direction of current which is coming outward, and this point direction of current which is inward, and this is outward point. This dot indicate that the current which is outward direction, and the cross indicate that the current which is inward direction. Clear? If we cut the toroid from its central part, the middle section, then the diagram will be look like. Then the diagram can be drawn. If we cut from its middle part, then this is the diagram, or this is the model of a toroid, and here this is the direction of flow of current in this way, direction of current, and this dot point which indicate that the current which is flowing outward direction, which is outward direction, and the cross indicate that the current which is flowing inward direction. Because this is the direction of flow of current. Clear? Okay. Suppose we have to find magnetic field strength. This is the center point O, and this distance which R, it is radius of the solenoid. Now we have to find magnetic field strength at point M at a distance R from the center of the solenoid. So at point M, first we have to find magnetic field strength at point M of the toroid. That means R is very greater than capital R. What is small r? Small r means distance from point O to point M, where we have to find magnetic field strength for toroid. And what is capital R? R means radius of the toroid. Clear? So according to Ampere's circle law, that is D dot dl over a closed integral, which is equal to mu naught times I enclosed. What is I enclosed? If we draw a Amperian loop of radius R, and this Amperian loop is passing through point P. Now this is the Amperian loop in the form of a circle, and this distance is also R, and this distance also R, and this distance also R. And this Amperian loop which is passing through point M, where we have to find magnetic field strength. Clear? Now we have to find what is I enclosed. I enclosed means total current within the Amperian loop. Here the current which is in outward direction and the current which is inward direction. That means same number of current which is flowing outward direction and same number of current which is inward direction. So net current. So here I inside or I enclosed equal to 0. That means B dot dl over a closed integral which is equal to 0. So magnetic field at point N equal to 0. Clear? So this point magnetic field strength is equal to 0. If you choose another point here N and which is distance R, so what is the magnetic field strength at point N? For this point, that means now we have to find magnetic field strength at point N. That is R is less than R. That is inside the point, and this small r which is less than capital R, radius of inside the toroid. Now this distance is R. This distance is R, where we have to find magnetic field strength. That means at point N, and this point is less than capital R. What is R? Small r means where we have to find magnetic field strength, and capital R means radius of the solenoid for radius of the toroid for ideal toroid. Clear? Okay. So if we use Ampere's law, that is B dot dl over a closed integral which is equal to mu naught times I enclosed or I inside. So what is I inside? I inside means total current within the Amperian loop. So first we have to draw a Amperian loop of radius r. So this is the Amperian loop, and this Amperian loop which passing through point N. Clear? So in this case, first we have to find I enclosed or I inside. What is I inside? I inside means total current within the Amperian loop. That means there is no current within the Amperian loop, because this is Amperian loop of radius r, and there is no current flowing inward and outward direction, because this cross indicate and the dot indicate the current which is inward and outward, but these are the current flowing which is outside the Amperian loop, but inside the Amperian loop, that is here I inside or inside the Amperian loop is 0. There is no current inside the Amperian loop. So the above relation can be right. It is B dot dl over a closed integral which is equal to 0. That is B at point N equal to 0. That means magnetic field strength at point N equal to 0. Now we will come the third point. Suppose there is a point P. There is a point P where we have to find magnetic field strength. So at point P we have to find magnetic field strength, and suppose this distance R. Now if you make a clear diagram, then this is the cross point and this center of O and this radius R. Suppose this distance is small r. Due to ideal solenoid, this thickness is very small. So for ideal solenoid, this thickness is very small. Suppose this radius is R1 and this radius is R2. Here R1 nearly equal to R2. That means this radius R can be right, this radius small r. So here capital R equal to small r, or small r equal to capital R. Now we have to find magnetic field strength within the toroid. Clear? Okay. Look at the diagram. It's the direction of flow of current. It's the direction of flow of current, because the current which is coming outward, this is inward. So if we use right hand thumb rule, then magnetic field inside the toroid, and it's the direction of magnetic field, and this magnetic field strength is maximum and constant along the, if this is concentric radius of the ring. Clear? And this is the direction of magnetic field inside the toroid. Okay. Now we have to draw a Amperian loop, and this loop which is passing through point P, and this is the Amperian loop which is passing through point P and radius R, and this is the direction of Amperian loop, and this is also the direction of magnetic field. If you choose this point, then this point, this is the direction of magnetic field, and this is the direction of dl element. What is dl element? Length element. Because the direction of length element is along the direction of Amperian loop. Because we chose this is the direction of Amperian loop, and this is the direction of magnetic field also here. So theta is 0 degree. If we use Ampere's law, that is B dot dl over a closed integral which is equal to mu I inside. That is mu I inside. So B dot dl, that is B dl cos theta over a closed integral. What is theta? Theta is angle between B and dl. So here at point P, B and dl angle is 0. If you choose another point here, then this is the direction of magnetic field and this is the direction of dl element. So theta is also 0 degree. If you choose another point here, then this is the direction of magnetic field. Then this is the direction of magnetic field inside the toroid, and this is the direction of amperian loop also. So this is the direction of B and this is the direction of dl. So here theta also 0 degree. If you choose another element, small element dl, and its length this direction, and here of the direction of magnetic field, so theta also 0. Each and every point the magnetic field strength is constant and theta is constant. So due to symmetry you can write that is mu naught I inside. Clear? So theta is here 0 degree each and every point due to circle. Here 0 degree and here also theta 0 degree because this is the direction of magnetic field and this is the direction of dl element. So theta each and every point is constant and that is equal to 0 degree. So you can write B dot dl cos 0 degree equal to mu naught times I inside, and the value of cos 0 equal to 1. So and B each and every point the magnetic field strength is same. So you can write B dl equal to mu naught times I inside. Clear? Okay. What is dn? So this is length element dl. So total length of the amperian loop which is equal to 2 pi r, and the radius are here. So you can write that is B integration 0 to 2 pi r, that is dl which is equal to mu naught I inside. So first we have to know what is I inside. I inside means total current within the amperian loop. So what is amperian loop? Look at the diagram, and this is amperian loop, and the cross indicate that the cross which is inward direction, and the current which is inside the amperian loop, but the dot which is outside the amperian loop. So inside the amperian loop we have to consider only this cross line. Suppose this is amperian loop and this is the cross, the current which is inward direction, and suppose this is first term, second, third, fourth, 5, 6, 7 and so on. Suppose there are n number of turns, that means for n turn and total length of the amperian loop, that is 2 pi r length, there are n turns. That means the toroid consists n number of turns. If this distance, this radius is r, then total length of the amperian loop which is 2 pi r. So 2 pi r length, there is n turn. So 1 unit length, there are n by 2 pi r turn, and this is equal to n. What is n? N means there is small n equal to number of turn per unit length. So number of turn per unit length. So n equal to total number of turn by 2 pi r, and which is equal to n, capital N equal to, it is n into 2 pi r. So this is the value of n into 2 pi r. Again we have to find I inside. I inside means total current within the amperian loop. This is amperian loop, and total current within the amperian loop, the current which is inward direction, but this dot point indicate outward direction, but this dot mark which is outside the amperian loop. So only we consider the current which is inward direction. If there is n number of turn and each turn consists I current, then n number of turns. So I inside equal to n I current. For 1 turn there is I current, 2 turn 2 I current. Similarly, n number of turn, there is 12 current, n I. So you can write here that is mu naught into I inside equal to n I current going through the amperian loop. So and this if we integrate and using the upper limit and lower limit, we can write b into 2 pi r. Clear? So the relation can be write B into 2 pi r, that is B into 2 pi r, which is equal to mu naught n I, and mu naught into what is n? N equal to n into 2 pi r. So 2 pi r into n I. Here 2 pi r cancel. So B equal to mu naught n I. So this is magnetic field strength at point B. That means within the toroid. So B equal to mu naught n by 2 pi r into I. Here this is magnetic field strength at point P. So there is 3 point N, and point P. At point M magnetic field is 0. At point N also magnetic field equals 0. But at point P, that means within the toroid or ideal toroid, that is B equal to mu naught n I. Clear? So this is all about the magnetic field strength for solenoid and magnetic field strength for toroid by using Ampere's central law. Clear?